FSC and chemistry too. Oh, okay, so actually, we were wondering, how do you does well? Yeah. You can have when you do. Yeah, I did always. And I was just like. This is right here. I sat down and I was like, oh. Yeah, I remember this. Like a picture needs a lot.
Okay. All right. Hello, everybody. Happy Monday. Are you all refreshed? No? Okay. All right. So let's have a little bit of a recap with chromatography. How would you define chromatography? Separation. So it is a technique used to separate components in a mixture. Once they can be separated, again, I'm going to repeat those for you. It have to be separated first, then you can identify, then you can quantify. So without components being able to separate from one another, you cannot do a detection, identification, and quantification. So first step is separation, and that's where chromatography come into play. What are some applications that you can think of? Emma?
Flavor.
Flavor. And what type of chromatography would you use for flavor?
Gas.
Gas chromatography. Very good. All right. What else? We talked about anything and everything. Remember? So you can do protein analysis. You can do fatty acid composition, which you will do in lab next week. You can do sugar and oligosaccharides. You can do vitamins. You can do organic acids. You can do pesticides. You can do antibiotics. Oh, the list is huge. Okay, so like I said, we will learn chromatography, then we will have a lot of applications that we will talk about later on in different chapters using chromatography. Okay, so what's the difference between a stationary phase and a mobile phase, and what is the function of each? Anybody want to give a yes, Al?
Stationary phase, the compound in the solution that's more attracted to it will stick to that. And the other compound in the solution, or multiple compounds, it depends on the difference in polarity of the stationary phase and the mobile phase. But the other compound will go into the mobile phase and it will elute faster than the stationary phase.
Exactly. So if I want to put it together, what Ali said, so the stationary phase is the phase where your components in a mixture are interacting with. So the stationary phase is not moving, and then you have components that you injected on the column, and they go down. With the mobile phase is the carrier. So the mobile phase is going to drive that movement, that mobility. And then the compounds in that mobile phase will start interacting with the column or with the stationary phase and will be delayed. Okay. And then the more strongly they interact with your stationary phase, the less they're going to move with the mobile phase. Okay. So, and then the components will separate based on how much they like interacting with the stationary phase. The more they like interacting with the stationary phase, the slower they're going to be in leaving. Okay. The less they like to interact with the stationary phase, the more they will be in the mobile phase, and the faster they're going to move down the column and leave. Okay. So the mobile phase carries the components. The stationary phase is there to interact with the components. So one is driving mobility and one is driving interactions. Okay. So how would you define extraction, and can you give an example in food analysis? extraction. It's the word as it entails, right? So you're extracting a component from a mixture, and you use a solvent that that component likes to be in. Okay, so like you're extracting fat for fat analysis. So you use organic solvent, hexane or ether or chlorophyll. So use organic solvent to get that fat out, to extract that fat out. So extraction is used to as a means of analysis, like the fat analysis, or a means of cleanup. So sometimes we need to do defatting before protein extraction or defatting before carbohydrate analysis. So cleanup or concentration. I want to do flavor analysis, but I need to concentrate those flavor components in a solvent that would get them out of that mixture. And then I can concentrate them and I can analyze. All right. What are three types of chromatography? Liquid chromatography is one. Gas chromatography is two, and third one, supercritical fluid chromatography. So these are different types of chromatography. We'll learn later on today different modes of separation within one type of chromatography. All right. What is the form of the mobile phase in GC? Gas. All right. What's the form of the stationary phase in GC? Liquid, solid, gas. The stationary phase, it can be solid, but also it can be a liquid layer coated on that solid support. What about partition chromatography or partition in liquid chromatography? So in partition chromatography, you have liquid stationary phase and liquid mobile phase. In adsorption chromatography, you have solid stationary phase and liquid mobile phase. And partition coefficient, any remembers that? Huh?
Okay.
It's yes, yes. Well, what does it mean? What does it give us? It's okay if you don't remember. But
Concentration of solute in phase one over the concentration of solute in phase two.
correct. So usually the solute is partitioning. It's partitioning in between the two phases, the stationary phase and the mobile phase. And usually on the top of the equation is the concentration in the mobile phase. And on the bottom is the concentration of the stationary phase, usually. But it's the proportion, how it divided between these two phases. So it's the proportional value. And it's a constant for partition chromatography. Okay. Very good. So as you study, make sure you go through these questions and make sure you're able to answer them, okay? So it will be good check for you. All right, so I'm going to cover planar chromatography first, and then column chromatography. And this is it for me with GC. I kind of gave you an overview. You already had 2 lectures with Gary, so everything I'm going to talk about mostly applies to liquid chromatography. Okay, so liquid chromatography can be planar or can be in column, but it's more common, the columns, and I'll talk about column liquid chromatography in a little bit. But paper chromatography is the type of chromatography that is used for screening. It's not very much applied. We see it more in educational setting, but the principle is you have a paper made of cellulose. So you have the cellulose as a support material, and usually you impregnate that paper with water. Very common the stationary phase is water, because the water now is your stationary phase that is supported by the paper, the cellulose. Okay. And then your mobile phase, bless you, your mobile phase is the immiscible solvent. So it can be hexane, for example. It's immiscible with water. So what happens is you get your piece of paper, and then you kind of have a draw with pencil a line about a centimeter or an inch from the bottom, and then you put your samples on it. M for marker, usually your standards, and then your different samples. It's very common to use to look at amino acids, for example, in an experimental or educational setting. Then you put your samples on that wetted paper, and then you put it in a chamber. We call it maturation chamber. And then you put your immiscible solvent, let's say hexane, and then the solvent starts going up, and your different components will move up with the solvent. However, if they were polar, they're going to like the water more than the hexane. They want to stick on the water on that paper and not move up as much. However, components in your samples that are not polar and like the hexane will move up with the solvent more or faster. So then they're separating based on their relative polarity or relative solubility in the different solvents. The water that is impregnated on the paper and the immiscible solvent that is the moving or the mobile phase. Okay. So if your samples are amino acids, they don't have colors, but if you spray them with anhydrous, then they will have different colors. Then you can see them separated after you spray them. Or if you're separating sugars, for example, you can visualize with autoradiography. I got stumbled here for a minute. You can do 2D as well. I'll explain to you what that means. So if you spot your sample and then you put your first solvent, and then they go up and they don't separate very well, so you cannot distinguishingly separate them, you can take this piece of paper, flip it 90 degrees, and put it in a different solvent. That your components will have different solubility in that solvent. Then you can see them separate better. So first dimension, they didn't separate as well. And then the second dimension with a different type of solvent, you get them to separate better. So you can do that. In order to give some sort of identification to your compound, you calculate an RF value, which is really the distance moved by each compound. So from where you spotted it on that line to where the center of that spot as it moved up, relative to the distance moved by the solvent. So you would visually see how far the solvent went up. And usually this is a constant. However, there are different conditions that impact that value. The thickness of the paper might impact the temperature in the chamber, the humidity in the chamber. And then how long the paper is, so distance that is available for the solvent to move. So all of these factors will affect the RF. Usually you have to run standards on the same piece of paper. You run your samples so that you can get the identification that is constant, because it's hard to repeat it. Every time you run it on a different paper, you might get different results. So that's why it's not really a very well used technique for quantification or for real identification. Less common used, you can take that paper and impregnate it with a nonpolar solvent, and the water is the mobile phase. It's not very common, but in this case, if it's run this way, it will be called reversed phase. Now we're going to go into what is normal phase versus reverse phase. So initially, the first partition chromatography was you have, this is so hard to, seriously? What? I don't want it. Okay. No, I must be weak. Okay. So usually we have, let's say this is a column, and if your stationary phase is polar and your mobile phase, stationary mobile phase, stationary phase, mobile phase, and this is polar, this is non-polar. This is called normal. Why they called it normal phase? Because that was the initial chromatography, partition chromatography that was used. And then they discovered, well, we can swap it really. We can have a stationary phase that is nonpolar, and we can have a mobile phase that is polar, so they called this reversed phase. Simply. Doesn't mean anything. It's just because initially it was polar and non-polar, and then they said, hey, we can do it the other way. We can reverse it. And then they called it reversed. So it's for no particular reason other than what came first and what was reversed. Okay, so paper chromatography can be reversed, meaning you can impregnate the paper with nonpolar solvent, and the stationary phase that is made of cellulose is made of glucose units, and glucose units has OH groups in them. You can derivatize the OH groups to carry an acid or a base, meaning it can be negatively charged or positively charged. Then you can run it as ion exchange. Okay, so you can run paper chromatography as normal phase, which is the most common, as reversed phase, and as ion exchange if you derivatize the OH group to carry an acid or a base. Okay. All these terms, we will talk more about them when we cover column chromatography. All right, so in reversed phase, paper chromatography, which one of these can be correct? Take a moment, think about what I said, and try to decipher. You don't want to guess? Yes. A and C, very good. So in reversed phase, you have your mobile phase is polar. So polar compounds will move more or faster than the nonpolar compound, so will travel the most. And then the RF value will be higher because what's RF is the distance moved by the compound over the distance moved by the solvent. So A and C is correct. Thin layer chromatography, also known as TLC. What does TLC stand for? Huh? That's new. The learning chain? The learning channel. Wow, I don't even know that there is a learning channel. You don't know that. I don't know. I guess I never learned on TV. I don't know. Yeah, but it stands for something else. What does it stand for? Other than that? Come. Yes. You got it. Okay, there's a story that I always tell now for the TAs, like, oh, we've heard it before. Um, so when I started teaching this class, my kid was in kindergarten. So I went one time after teaching chromatography, go to pick her up. She's sitting in the lap of the teacher, and I looked at teacher, what's happened? She goes, your daughter needed TLC today. I was like, thin layer chromatography? Why would my daughter need thin layer chromatography? It was the first time I got introduced to tender love and care. So now I know this term as tender love and care, and which also stands for, what did you say? The learning channel.
False. Yeah.
Do you guys know what she's talking about? No.
What? TLC, like 90 Day Fiancé? Yeah, I think Orders was on there too. Yes, Orders. My sister's good.
So you all know what they're talking about? You do, William? No. Okay, so William doesn't know. It's not just
It's like bad.
it's bad American TV?
Yeah, not very much fun. Yeah, there's no learning.
Okay. So it's good that I don't know of it then. All right, so thin layer chromatography, similar principle to paper chromatography, yet that much better. Why is it better? It's first of all, let me tell you, have you seen thin layer chromatography before? Yeah? No? Okay, I should have gotten a sample. So in the olden days, my day, we used to have a square of glass. Thin glass is the support, and we used to just wash it really well and then wipe it with alcohol, and we prepare silica solution or paste, and then we kind of have a roller and we roll silica on this plate. Now you can buy them already pre-made either on glass or more commonly on aluminum. So squares of aluminum is your support, and then you have a very, very thin layer of silica gel on it. So you can also have support, if not glass, not aluminum, it could be plastic as support. But what makes them better is the silica gel has very fine uniform particles. So when you spread it in a very thin layer, you would get really very good consistency of these particles. Then you have better resolution, meaning better separation between the components than what you would get on paper. So you can control the thickness better, you have better, the amount of liquid impregnation would be more consistent between the different plates. So you have better reproducibility in general, better separation. And faster because small particles, very thin material. So you have faster movement of the mobile phase, travels faster. Yeah. So this is basically what I just explained. Mostly it's silica, but there are alumina and cellulose, but silica is the most common layer of stationary phase, or it can be the layer that we impregnate with water. Okay. Most commonly, normal phase can be reversed if we impregnate with nonpolar solvent, or the silica can also be derivatized to carry acid or base to be charged or ion exchange. So once separation happens, if it is amino acids, we can use ninhydrin. Sulfuric acid is common. You can spray, and it's a very concentrated acid, so it burns organic matter. So you get like burnt spots where you have organic matter. So that you can use. You can also use a fluorescent. So you can make it fluoresce, make your compounds fluoresce and measure fluorescence. Or if you can radiolabel something or your compounds are radiolabeled, you can measure radioactivity. Now, a very common use is for different fats. So here's like phospholipids, monoacylglycerol, diacylglycerol, free fatty acid, triacylglycerol, and then your sample. So these are standards. And then you can look at your sample to determine what you have in there. Actually, they use it in experimental nutrition class. If you are a double major, you might have done that or not yet in the spring, maybe. And they do that fat composition in blood, in serum, in blood samples. Did any of you do that? No? Anybody? What's that? You're gonna take it next time? Yeah. Okay. All right. And then you can determine sometimes semi-quantitatively, you look at the intensity of these spots by looking at the densitometer. So you can determine the density, and if you have standards, you can semi-quantitate your components. Or you can take that spot, scrap it off, and put it in a like a syringe that it's filled with silica or something, and then wash it down and take it out and then measure the concentration using different method of analysis, spectroscopy, for example. Okay, that's it. This is all I have to say about planar chromatography. Any questions? All right, now we go to business. We talk about column liquid chromatography. So I'll talk about the low pressure column liquid chromatography, and then we will have, if not this week, next week, a lecture on high pressure or high performance liquid chromatography. Low pressure liquid chromatography, you get columns of different sizes, width, length, and then you fill them with your stationary phase under low pressure. So later on, I'll show you, or in lab next week, you will see columns, HPLC columns that are filled under high pressure. But these columns are filled under relatively low pressure, and they come in all sizes depending on what we want to do. So do we want to separate large quantity and we don't care about purity and we don't care about perfect resolution? Then we use columns like this, or even bigger and wider. So if we really want to separate with some sort of good separation, good resolution, we tend to use longer columns. Longer columns allows more interactions and more separation between the different components. I'll talk about that resolution later on, maybe next lecture or the one after that. But the longer and the narrower the column, the better separation you get, the sharper peaks, chromatographic peaks you get. Whereas larger columns are usually used if you don't really care about purity and you just want to separate large amount of sample. So what's happening over there, ladies? I like a good laugh. No? She said cooked. What's that? She said, what about the columns? She doesn't want you to say. Okay. All right. Well, so you prepare your stationary phase and you use a pump, a peristaltic pump, to pump in your stationary phase with a specific rate and pressure to fill it up. And then it's ready now. You have your stationary phase in a column, and then you will have a specific mobile phase for whatever you're trying to separate. So now I wanted to talk about what we mean with isocratic versus gradient mobile phase and demonstrate it here. So if you have one type of mobile phase, forget about this for now. If you have one type of mobile phase, let's say it's a buffer, or it is water, or it's 90% acetonitrile, whatever it is, it's just one type and then you're running at a particular rate, 1 mil per minute or 10 mils per minute, depending on the size of the column. And it's the same mobile phase, we call it isocratic, meaning you're not changing anything over time. It's the same mobile phase, go in, separate, you have your mixture, it gets separated, and then you don't need to do anything with the mobile phase. If you have compounds that are very different in the way they interact with the color, and then you have something that interacts very strongly and something that interacts loosely and comes out in 10 minutes. And then you wait and you wait and you wait, and the other compound takes an hour to come out. What do you do? Remember the justice example? What do? Do you wait for the little girl to take her entire sweet time to come out and maybe never come out? Or what do? Add something. So you change the composition of your mobile phase to attract that compound that interacted so strongly with your stationary phase. So you give it something that it likes so that it moves faster down the column, and you don't wait for 2 hours. You speed up your analysis. So this is gradient illusion. When you change the composition by adding another solvent here, and sometimes you can have 3 solvents, sometimes you can have 4 solvents, but you start mixing and changing the composition of the mobile phase. This is called gradient mobile phase. What you're doing is changing the strength of the mobile phase. And that means you're increasing the strength. You're making it stronger for the compound of interest. No matter the direction of how you are changing your mobile phase, once you change your mobile phase, you're increasing its strength with respect to that compound so that it comes out. Let me give you an example. So if you're running reversed phase, which you will do next week in the lab for a caffeine. So what you start off with is 99% water, DDW, this double distilled water. Okay, and then 1% acetonitrile. That is the composition of your mobile phase. Then you have a column that is a C18 column, meaning it's a silica column that has it's derivatized with a chain of 18 carbons, a compound with 18 carbons. That makes it less polar, that makes it nonpolar. So this means it's nonpolar. So now you have your compounds interacting. So you have your mobile phase, and then now your compounds are interacting with the column and taking a very long time to come out. Your caffeine is interacting, and then you want it to come out. What do you do to this mobile phase? So it's 99% water, 1% acetonitrile. What do you try? What do you do? Increase what? Of what? Of the acetonitrile. So I increase the concentration of the acetonitrile up to 30% acetonitrile, I believe, was the, and then 70% water. Oh, 70% water. I changed the concentration. So I increased the strength of my mobile phase by changing the concentration. But increasing the whole, this is very important and shouldn't confuse that. Increasing the strength does not always mean you increase the organic solvent. No. Increasing the strength, anytime you change the composition in any direction, you are increasing the strength of the mobile phase. So the other example would be if I have a polar stationary phase. Polar. So impregnated with water, silica impregnated with water. So it's polar. Now here I have, let's say I have acetonitrile, 70%, 30% water. That's my mobile phase. How do I increase the strength of this mobile? So this is normal phase now. Normal phase or helic. Hydrophilic interaction chromatography, either. So, and this one is reversed phase. So this is normal phase. This is reversed phase. Okay. Here I start with acetonitrile 70%, water 30%. How do I increase the strength of this mobile? In the water. Increase the water. So I increase the water here. In this case, I can have 70% water and 30% acetonitrile. So in both cases, I increase the strength of the mobile phase, but in a different direction. So it's not always in one direction. The whole purpose of it, to have a gradient elution, is to make that mobile phase stronger for the components you have interest in separating. That's what it means when we say increasing the strength of the mobile phase. It doesn't mean increase the organic solvent. It depends. Yeah.
Changing the phase to get that last compound out, how does that affect the analysis then? Is it based on time?
Yes.
Separation? So
Yeah.
how would that affect the analysis of the time that it would take with a different mobile phase compared with the time that it took with the original?
Yeah, if I didn't change, if I'm going isocratic with the original, it will eventually come out because everything is moving. Your mobile phase is moving, your components are equilibrating in and out. They're moving, but so slow because they so much love the stationary phase. When you change the mobile phase, you put in there an element that the compound of interest would now like to spend more time in it and go down faster. So instead of an analysis of 2 hours, it could be 20 minutes. You just made it faster. Good question. Any other questions? Yeah, it's very important to know that increasing the strength is different in every case. It depends on what the compounds is, what the stationary and mobile phase are. Then you would know which direction you would want to change it. Do I change the water increase or do I increase the acetonitrile? It can be either, depending it's reverse phase, normal phase, ion exchange. We will learn in ion exchange how you have a gradient elution as well. So gradient elution means it's meant to increase the strength of the mobile phase, to enhance movement in the column, shorten your analysis time. Okay. Question? Supercritical fluid chromatography, only one slide on that. It's not as common as HPLC and GC, but it is used. In this case, you are using a mobile phase at above critical pressure and temperature. So basically, CO2 is gas. When you compress it, you pressurize it. So it is above its critical pressure and also above its critical temperature, it becomes fluid. So it will have the characteristics of a liquid, but it is much less viscous than the liquid, the actual liquid, and it has high diffusivity, meaning it's just the components in your sample can move in and out very, very easily. So it enhances resolution, you get better separation, sharper peaks. So that's its advantages, and it's commonly used for compounds that are nonpolar, but they don't have thermal stability, and they are not volatile, so they're hard to be analyzed by a GC. So when sometimes we add methanol to liquid CO2 to kind of have a diversity in the different compounds that we can separate. So if compounds are a little bit polar, not completely nonpolar, adding a polar organic solvent like methanol will help. So sometimes you just run it with CO2, sometimes you mix with methanol, depending on the components. And the stationary phase that is used in supercritical fluid chromatography is very similar to what we would use in HPLC, and we'll talk a lot about those later. And the detectors that are used are very similar to those that you learned with Gary. So the detectors would be FID, for example, or thermal conductivity detector, or any other detectors that are used with GC. Okay, that's all about that. Now I want to move, I have a few minutes to just introduce this and talk about it in more detail on Wednesday. So now I want to talk about mode of separation. So we talked about type of chromatography, HPLC, GC, supercritical. Now I want to talk about mode of separation, which is the physical-chemical principle of chromatographic separation. So on what basis we have interactions, or what types of interactions? Are they physical interactions like in size exclusion or molecular exclusion? That means the same thing. If you see size exclusion or molecular exclusion, that means the same. Sometimes you see gel filtration, it's the same. So this is physical. So that means it's based on the size only. Chemical is you could have based on specific chemical interaction with a stationary phase that is solid. So either ionic interaction, like this is ionic interaction, that's still adsorption chromatography. Ionic interaction, or hydrogen bonding, or hydrophobic interaction with a solid phase. Or partition chromatography, which we already talked about. So two liquid phases, you have your support, and then the impregnated with a liquid layer, or bonded with a liquid layer, and then you have the solutes or the components partitioning between a liquid mobile phase and a liquid stationary phase. And then here we have the affinity chromatography, where you have kind of the lock and key. So it's like enzyme and inhibitor, or enzyme and substrate, or antibody and antigen. So interactions are hydrogen bonding, electrostatic, hydrophobic, van der Waals, all types of non-covalent interaction. So the stationary phase in this case is a solid. So affinity is part of an absorption chromatography. Ion exchange is part of adsorption chromatography, and there's also hydrophobic interactions is part of adsorption chromatography. So what I want you to learn here is there are different physical chemical basis for separations based on how the molecules in your solution or in your sample is interacting with a solid phase, a liquid phase, just based on size or based on chemical interaction. All right. So I guess I will stop here today and then we'll continue next time.